there are good reasons for doing all of this, because we felt we needed a very low latency. This was the market, this is our end users telling us that we wanted a really low delay. That was a big problem that we faced in what we were doing. With digital technology, you can also have a high dynamic range and also very linear aspects of that. Now, in the current UHF spectrum, we're talking 470 to 800 megahertz. We are sharing all of that spectrum with digital television. And there are good reasons why we use that spectrum, because it has good propagation characteristics. If you went up at 2.4 gig, the body absorption is far greater, you get far less range, and of course 2.4 gigahertz is full of Bluetooth, Wi-Fi and everything else mobile seems to emanate in that band. So UHF is still a very important aspect of the spectrum, which is very useful for wireless microphone systems. The bandwidth is being reduced all the time. In Europe now, we will be down to the 470 to 700 megahertz. In the US, we've also lost all of that aspect of it. So it's down to 130 megahertz. There's more and more regulator pressure around the world for wireless microphone users to make much more efficient use of this spectrum. And you know, it's when I've sat in meetings with Ofcom, which is the UK regulator, they don't have an understanding of the technical aspects. They don't have anyone technical. They are only interested in economics. How much can we get for that spectrum? And the mobile companies have the deepest pockets. And being smaller manufacturers, even with the likes of Sennheiser and Shure, we are still considered small. And the technology that we develop has a finite amount of resources that we can spend on this. So we mask, as you see, allows a lot wider modulation, or it did until January of this year. As the FCC have come to terms with the fact that, you know, they need to also enforce people to make much more efficient use of this spectrum. As from January 2018, FCC all American products are required to meet the ETSI mask. So they all need to meet the very tight regulations. I suppose the aspects that that this is all required to meet is the ability to put more channels together. And using this mask, it's still only 8 to 10 analog channels. There are certain manufacturers who are looking to try and use lower bandwidth on the RF channel, but that also has compromises in either performance in terms of the dynamic range of the audio, and you are still, if you're in FM analog, you are still limited by the intermodulation effects. Why digital? When we started down this road, a lot of people said to us, why would I want digital? Wireless microphones are essential in today's production techniques for health and safety, for the number of multi-camera shoots have now changed everything. Everything has to be done faster and quicker and at a lower budget, and that means everything needs to be done quicker. And well-engineered digital systems bring many advantages, especially to address the spectrum challenges that we have. We have improved audio quality. We have very few analog modulation. You can also squeeze in more channels working together, depending on the scheme that you've chosen. Ratio. So you can provide, you can have up to a 10 dB greater immunity for interference. That's not to say that there isn't interference which will affect the digital systems, but instead of having a much greater swamping of your analog systems, you will, with digital systems, you will get a reduced range, but it's still a very clean channel in an RF intensive environment. And of course, with digital systems, you will have great signal until the signal actually drops out. Whereas with FM analog, you will hear the noise floor come up, and you know that's starting to become an unusable signal at that time. For the user, there are numerous advantages. As I said earlier, the digital systems can operate near frequencies or where there's a lot of RF energy much better than analog systems. And because of the implementation of very linear output stages on the transmitter and conversely linear input stages on the receiver, you can keep the intermodulation to an absolute minimum. It's not to say that it's intermodulation free. There are intermodulation effects, but they are far more reduced in a digital system than they are in an analog. And then, of course, there is a lot more immunity from effects of non-linearities and spurious signals. When we started down this road in 2005, we investigated the various modulation schemes. But the aim was to design a system which has the minimum latency, equal or better audio quality, equal or better range, meeting the ETSI standards, and working on standard batteries. Not batters, as I've spelt there, should be batteries. And all of these things were a big challenge, because effectively, if you're looking at 16-bit CD quality, you're looking at a bit rate of about 784 kilobits. And now trying to get that into a 200 kilohertz channel is a big challenge. It's either done by complex modulation or a compression technique. So, and we knew in this market that we're in, people just cannot accept artifacts. We'd seen what effect minidisc had on the broadcast market, and psychoacoustic compression techniques are not for this market either. So it was a big challenge to find not only a modulation scheme, but also to look at the various compression techniques and see what could be done. And the result of effectively 12 years of research was to produce a system which only has 2 milliseconds end-to-end delay. It has better audio quality. I've put on the 50 hertz, but it's actually flat down to 20 hertz. It has better RF performance in terms of keeping the quality of the audio before it actually starts to mute. Use of standard batteries, and as the regulators have been pushing us for many years, making much more efficient use of the spectrum. So we've managed to get 20 channels operating in an 8 megahertz TV channels with even carrier spacing. So every 400 kilohertz, you can put a channel up and not worry about the intermodulation effects. The receivers have 224 megahertz switching bandwidth, so it will cover the whole UHF band, and the transmitters are banded. And the reason why they're banded at the moment is because the linearity requirements on the output stage, and of course current consumption, because digital is power hungry. One of the other aspects, of course, is multipath interference and diversity. So this is always something that we've always concentrated very hard on, was getting receiver sensitivity and making sure that the diversity technique is implemented in a correct fashion. In the diversity techniques that we've always used in all of our products, we've always had two separate receivers utilizing what's known as selective diversity or space diversity. In addition to this aspect, we also, in the digital domain, give the carriers a weighted sum. We can sum the RF channels as well. So you can take, there is information still, even when a digital channel has low RF. In an analog world, we would always switch to the highest signal on a diversity receiver. In the digital world, you can actually take the bit stream from a low channel and do some mathematical progression to give us a weighted channel, and actually add that to the good channel and implement another aspect of it. And combining ratio with the frequency aspect as well helps enhance the standard true diversity techniques. And we think that also results in a 3 dB improvement in the sensitivity on the receiver, which in receive terms is the same as doubling the output power on your transmitter. So we've always been very good with selectivity and sensitivity on the receiver, and that also applies in the digital world as well. So it also helps to maximize the robustness under difficult conditions, and that has been proven to be a point. This is a spectrum plot of 10 A10 channels in occupying, as you can see, just 4 megahertz without loss of quality, without compromising this is all set to 50 milliwatts of output power. So you can see the spectrum is actually very clean. You've got very clean carriers at 400 kilohertz spacings. If you did this with analog, unfortunately I didn't have enough time to put some analog systems up to show you the spread of the spectrum of the spirits produced. But that's 10 channels in a 4 meg. Each of those graticules are 1 megahertz apart. So it's a very tight spectrum. And that's 20 channels in 8 megahertz. That's the full bandwidth there is 10 megahertz. But you can see, again, very clean carriers due to the linearity of the RF power. And that shows you just outside of that 8 megahertz. So you can see you've got an occupied area in the middle there with very clean outputs on either side. So in theory, you could take that 20 channels and replicate it in the very next TV channel and still be able to work. We still need to work out whether that will probably have some effect on the RF density, and if you're looking at trying to work with the near-far effect, that will also have an impact, but it won't be as great an impact. So there will be new rules as to the spacing between a receiver and a transmitter, and of course receiver antennas. But in theory, if you have that spectrum available, you can put another 20 channels next to it. So your spectrum density does indeed go up. What next? There are systems out there with narrow FM channels which can be implemented, but there's always going to be compromises. It's either dynamic range, audio quality, and other aspects. But all analog systems still require careful frequency planning because they still suffer from intermodulation effects. The high-density digital systems will compromise on audio quality or increased latency. We've looked at various other products in the marketplace, and there are certain aspects of those which will be a compromise. And the market that we're in, it's all about high quality. It's got to be broadcast and with good dynamic range and without any issues with that. People have said digital is power hungry, and there is no doubt digital is very power hungry, but the advantages are very clear. It is the way that things are going to work. And the digital aspects is the future, because in an ever-crowded spectrum, we are going to have to work with more channels in less space, or work alongside other high-energy RF situations. And we believe, certainly from the work we've done, that digital is the way forward. I've just put together some various parameters we've implemented on the A10 channels with great audio quality, dynamic range, higher channel density, 2 milliseconds end-to-end delay, 48-volt phantom powering on the balanced input, real-time clock, built-in recorder, and a very accurate time code. And the A10 systems can also be controlled via Bluetooth 4. The receiver also has tracking filters, and the receivers can be used independently, so that you can have one transmitter down at 470 megahertz and the other one at the other end of the spectrum, and both have independent tracking filters. Its sound device is super slot compatible, analog and AES output, and a very simple menu system as well. Thank you. And if there are any questions, please feel free to ask.
Donc, s'il y a des questions, je pense que Kish sera ravi d'y répondre. Ah oui, alors s'il y a des questions, il faut utiliser les micros. S'il n'y a pas de questions, on passe à la suite, hein, mais si, là.
Good afternoon. About the power hungry, what would be the difference between these new digital transmitters and an analog transmitter, considering the same battery inside?
The big thing with the FM analog is that it uses super heterodyne technology. So it uses the non-linearity aspects of a transistor to achieve that. There is a mixing in there, and of course it's you can get the output stage is very efficient because you're introducing these non-linearity in the FM systems. So from that aspect, you're not drawing much power. It was mainly only taking about 20% of the actual power on the circuit. Whereas on digital systems, you require to have because you're transmitting digital bit streams, you need a very linear output stage, and that's probably 50% of the power in your transmitter, and conversely on your receiver, that's also the case. So you need to be able to have a very linear input stage so there's no distortion of the digital bit stream, because as soon as you distort that digital bit stream, you get all sorts of scrambling effects, and you just don't get the clean audio that comes out at the other end.
D'autres questions? No. Ok.
Je vais répondre en français. Moi, j'avais une question sur la latence. Je voudrais comprendre pourquoi elle est plus importante quand on rentre en numérique sur le Cantar. Elle est de l'ordre de 5 millisecondes, alors qu'effectivement, quand on rentre en analogique, elle est de 2 millisecondes. Voilà.
The question is about the latency, and he is surprised that the latency is more important, around 5 milliseconds, when you use the digital output on the counter than if you input on the counter, compared to if you use the analog input, and it's 2 milliseconds. Yeah.
Yeah. It's because of the modulation. The way that the modulation scheme is done, it's absolutely integrated with all of the audio as well, and because we are actually having to come from analog back into a digital bit stream, so you're adding the delay of the AES. So on that's why it's almost double.
Parce qu'en fait, on émet sur c'est du 44.1. En fait, sur l'enregistrement sur la carte, on est en 44.1 16 bits. Et effectivement, sur la sortie numérique, on est sur du 48K 24 bits. Alors, je sais pas si c'est les temps de conversion.
You have some one more converter when you use the digital input on the counter?
Yes.
This was that. Yeah. Une autre question?
First of all, congratulations for all your devices you provide us from such a long time. I want just to, if you can give us a more accurate answer to the power consumptions question. It will mean an average consumption of how many percent more?
if we consider that the digital transmitter is probably around about 1.1 watt of power, and the receiver is 4.2 watts of power. I think it's about almost double the power compared to an analog system.
So it's divided by the same order, the time we can use a transmitter. We are switching from 4 hours to 2 hours.
Yes, essentially, yes, yeah.
Yeah, but it's not true, because I use it and you can work 5 hours with the same battery. It depends the level of the power emission. You have 3 different, you keep that, huh?
3 different power levels.
So if you use the mid power, you have enough to have a good range, and you can keep your battery like the analog one, approximately, if I can say that.
Yes, yeah.
Most of all, from my point of view, one thing very important in your products are the shape of the mini takes.
Yes.
Because it's so friendly user for the actor when you are going in the dress of a woman. So sometimes it's very touchy. So yes. I'm really urging you to give us the opportunity to have the same in digital.
Yeah. The big challenge with all of this is, we understand, we know that people love the shape of the mini transmitter, even though overall it may be bigger than competitor products, but it's the curves which people love, and we want to ensure that also goes on to the next generation. Our big problem is the balance between the battery life and what we can achieve with digital technology. So we are very aware of the requirements that the film and drama want from something in the mini transmitter.
Une dernière question peut-être, on a encore un tout petit peu de temps, sinon on passe à la présentation d'Aretech. Ah, pardon, excuse-moi.
Hello. I would like to know if the size of the transmitter is actually depending of the audio quality, the batteries, the number of channel or other technology, or maybe everything, and if it's actually for you the way to try to make smaller and smaller transmitter, or maybe if it's not the good way. For example, other label made very small transmitter actually. It's a good way to use, but it's not maybe the best technology. What is your idea about this?
I would say in all of our transmitter designs, the batteries are always going to be dictating what we are able to do in terms of the size of the transmitter. And even this one, probably more than half of that is battery compartment. So as the technology develops, of course, there will be greater integration of. We're getting more towards software in these units. So you're looking at DSP processors or an FPGA, and we are a small market in terms of the world market. The audio, professional analog, professional audio market is a very small industry. And we are very much dependent on what we feed from the telecommunications market, etc. So we always look at the silicon from that aspect of it and see what we can actually achieve into as much greater integration as we can. Of course, the RF is still very much very discrete technology, whereas the mobile phone providers, of course, everything is integrated into one big IC, and they spend hundreds of millions in development. Being a small company, we are dependent upon what we have in the market, and so we are getting towards, I think even in the analog world, we still had pretty much half, it was a split 50-50 silicon design, piece circuit builds, and battery compartment. And the battery technology is evolving greatly, so I think there is an opportunity in the next product to try and squeeze it into a smaller product, but its design is always a compromise, and what we can achieve with what the end users want and what compromises they're willing to give up on as well, because it's never going. We're never going. If I asked every single opinion here as one in the room what they would like in a transmit, I'd have a very long list. It's then deciding which are the important factors and what compromises we can make to get that integration in a tighter, smaller product. And of course, batteries are always going to dictate the size and shape of something that small.
Thank you, Kish.
Thank you.
Thank you very much.
Thank you.
Maintenant, j'ai oublié ton prénom, voilà, Clément de Aretech va nous expliquer un peu les évolutions des produits digital Zaxcom. C'est là. Ouais. Tiens, il faut que tu mettes ça. Je suppose sur tes oreilles.
Merci pour l'AFSI de nous avoir invités pour une petite présentation des nouveautés des Zaxcom. Je ne vais pas revenir sur les techniques numériques que nous a expliqué Monsieur Patel. Elles s'appliquent aussi pour Zaxcom. Je vais juste montrer un petit retour sur ce